This PowerPoint walks through the worksheet for Module 3. The objectives of the worksheet are to practice using longitudinal data to calculate an incidence odds ratio and a risk ratio, and to replicate your crude and adjusted odds ratios that you have done with a chi-square analysis using logistic analysis. Finally, we will introduce the test for effect modification using logistic analysis and an interaction term. The first question is using the longitudinal variables from the dataset given in Module 2 to explore an exposure and outcome longitudinally. The first two questions relate to testing whether adolescents who reported they needed but did not get care have high blood pressure in the later survey. The worksheet includes the syntax to create a binary yes-no variable for blood pressure based on clinical definitions. It uses the needed but did not get access to care as given in the data, which is already binary. Use the syntax within the assignment to create the binary variable and to get a 2x2 table with the odds ratio and confidence interval to test the association. Fill in the values for A, B, C, D, the odds ratio and confidence interval, as well as the p-values. Be careful that you don't mix up the numbers. SPSS gives the zero condition in the first column and row, whereas in the tables, you will need to have the yes condition in that place. So the SPSS 2x2 tables are inverted. Your results will be the same, but the tables are backwards. In question 2, you are taking the results to get a risk ratio. In epidemiology, we did not talk in depth about the risk ratio. It is the incidence or risk in the exposed compared to the incidence or risk in the unexposed. In words, the formula is given here. Within the exposed group, how many developed the outcome divided by the total number of the exposed. This is then given as a ratio or divided by the risk in the unexposed, calculated as the number who got the outcome in the unexposed group divided by the total number in the unexposed. Here the formula is given based on the values for A, B, C, and D in the 2x2 table. Finally, these are the numbers based on the worksheet example, showing how the information in the tables can be used to answer parts A through E and to calculate the risk ratio. From question 3 onwards, all explorations are cross-sectional. It happens that in the survey, most of the exposures in adolescents were not clearly related to outcomes in early adulthood, but the cross-sectional variables showed more clear relationships. Use the syntax to create the variable for high blood pressure as a 0-1 variable. Run the syntax to get the output for the odds ratio, confidence interval, and p-values for the associations and paste these results into the assignment. Answer the questions related to the output. So even though the output is given in the results, write the odds ratio and confidence interval so it is clear you know how to find this information from the output. In writing a sentence describing your results, make a statement that is consistent with the odds ratio. If the odds ratio is near 1, describe the association as being near unity or there being no association. If the odds ratio is greater than 1, use the phrasing that the exposed are 1.05 or however large the odds ratio is, times more likely to have that outcome. If the odds ratio is less than 1, describe the association as being, for example, 0.7 times as likely. Or if it is easily made into a fraction, you can talk in terms of 0.5 or half as likely, or 0.3 as a third as likely to have the outcome. In reporting statistical significance, conclude whether the odds ratio result shows a statistically significant difference and support that with the confidence interval. Question 4 is to use the data to fill in a 2x2 table into an odds ratio table format and to double check the result by hand. This is always a good idea. Sometimes you might accidentally use a version of the variable that is flipped around. So using one 0-1 variable and another 1-2 variable will show the inverse result of the odds ratio. Your odds ratio calculation by hand should match up to the results from your SPSS output. If it doesn't, please contact me. In question 5, we repeat the analysis using logistic regression. The result will be exactly the same as the odds ratio and confidence interval for the 2x2 table results, but running logistic regression allows for testing multiple confounders and a test for interaction. Always explore your data using 2x2 tables before running a logistic analysis. To run the logistic regression, go under Analyze, Regression, and select Binary Logistic. The pop-up window will look like the one shown here. Add the created hypertension variable as your dependent variable box, shown here at the top. Next, enter your main exposure, not having insurance, into the block 1 of one box. Next, select on the Options category to select the 95% confidence interval. So on the right side, the third button down, click on Options, and you will see this box appear. This slide shows the option box for the logistic analysis. By selecting the confidence interval for the EXPB, that's the exponential beta, set at 95%, you will get the 95% confidence interval. The other options are pre-selected, but if in your output you don't see the B value, go back here to select the option, Include Constant in Model, right at the bottom. It's already checked. This slide shows what the output looks like in SPSS. Most importantly, the B represents the beta coefficient, or the e to the B, as in our exercises early in this term. The odds ratio is in the column marked EXPB, or exponential B, which is the back transformation of the logarithmic function. So remember in our early exercises, we did e to the b. So in looking at the full output pasted below, the b is 0.011. The p-value can be found in the column SIG, which stands for significance, which is the p-value, 0.935. And the odds ratio, which can be found under EXPB, is 1.01. The confidence interval is given on the far right, identified as 95% confidence interval for the exponential b, or e to the b. The next step is to get an adjusted odds ratio using the crosstabs function, as you did in epidemiology. Use the syntax in the worksheet and paste the results into your SPSS syntax and run that. Use that information to report on the adjusted odds ratio and confidence interval in your answers in question 6. The results will be a good way to double check your next step when you get an adjusted odds ratio using logistic regression. Always check the data with 2x2 tables before proceeding to logistic regression to be sure that the results are logical and to be sure that none of your cell sizes or subgroups has less than 5 persons. If so, if you have too few people, we consider the final estimate, or the odds ratio, to be unstable because a very small number of people can have a large influence on the result. This is output showing how to read the logistic regression results. Although I'm using a different exposure and confounder as in the example worksheet, after running the syntax you will get output below that looks like this. Your first question will probably be, which row do I use for the B, the odds ratio, and confidence interval? The most important row is the row related to your main exposure. In this case, needed but did not get medical care. But in your worksheet, it will be having no health insurance. After entering the confounder, the B, exponential B, and confidence interval might change. If there is no change, there is no confounding. If there is a change, the question is, how much does it change? We're looking for the change in the B. We call that the beta coefficient for a logistic regression to test the confounding. Last semester we used the 10% change criteria, but in that analysis we only had odds ratios. So we looked for a 10% change in the odds ratio. Here we have better information, and we can use the beta coefficient instead. We use the beta coefficient because it is a more sensitive test of confounding. It captures more confounders and gives a more balanced test for confounding, making it appropriate for odds ratios below as well as above 1. The assignment will ask for the crude B, adjusted B, the difference between them, simple subtraction, and percent difference to guide you through the process of assessing whether the inclusion of a confounder variable alters the results. The final step in the assignment is to explore effect modification. As we discussed in epidemiology, interaction is the concept of whether the effect of the exposure is modified by another variable. We call an effect modifier. The first step is to explore that possibility by getting odds ratios stratified by the effect modifier. In other words, getting odds ratios stratified by male versus female. Is the effect of having no insurance on high blood pressure different in men and women? We can see this from the odds ratios when they're stratified separately by male and female. The syntax in the worksheet splits the file and runs the crosstabs for an odds ratio for men and a separate odds ratio for women. The two odds ratios will already be adjusted by the confounder using the layering function. The output from the crosstabs are the stratified by male and female, adjusted odds ratios, and confidence intervals. You will get one odds ratio and confidence interval separately for males and then from females. The result from question 9 can show you whether odds ratios for men and women are different from each other. But is the difference statistically significant? Could that difference be random chance? In epidemiology, we didn't have a way to test that question statistically. Using a logistic model, it is possible to answer that question by entering an interaction term. The interaction term multiplies one variable against the other. In this case, the variables are 0, 1 variables, so multiplying them together will mean that the interaction term stands for having no health insurance, the main exposure, and also being male, the effect modifier. The logistic model tests the statistical significance related to this interaction term. Before we look at the results, it is important to remember that the model you run is only useful to test statistical significance for the interaction term. A second thing to consider is that some researchers use a more generous threshold for the p-value of an effect modifier. Some use a p-value cutoff of 0.20 instead of the more conservative 0.05 cutoff. Remember that the p-value is designed to err on the side of caution. The argument for a more lenient cutoff is when looking at the interaction, we are also concerned about the risk of missing a true interaction because of an overly strict p-value. The statistical significance tells us whether our findings could be related to chance. But if we have an interaction term with a p-value of 0.06 and the odds ratios are different in a meaningful way, we would be remiss to ignore this result. This is an example of the output for the full model, which includes the main exposure, confounder, the effect modifier, and the interaction term. It is important to include both the main exposure and the effect modifier in the model. Otherwise, it is not possible to compare the effect of both together, what the interaction term does, to the effect of the exposure and the effect modifier separately. In looking at this table, the focus should be on looking at the row of your interaction term and finding the p-value. Look for the column marked SIG for significance. In this case, the p-value is 0.139. It would not meet the 0.05 criteria, but it meets a less stringent 0.20 cutoff. Here, we say the interaction term was significant at the 0.20 level. The rest of the model does not tell us anything of value, so if we find the interaction to have been important, we use the stratified results as the final answer. That would be the model given separately for males and females and adjusted for any confounders. So those are your results from question 9. Thank you.